What if the universe didn't begin with a bang, but with a quantum maybe? Picture this, a moment before time itself, when reality wasn't solid, but a shimmering haze of possibilities. A place where the rules of physics as we know them hadn't quite decided what to be yet. This isn't science fiction, it's one of the most mind-bending ideas at the heart of quantum mechanics. The concept is called superposition, and it suggests that particles can exist in multiple states at once, only settling into a single reality when observed. Now imagine scaling that up. What if the entire universe started in a state of quantum superposition, a cosmic uncertainty that collapsed into the reality we see today? For decades, scientists have grappled with the origins of everything, but the deeper we dig, the stranger the answers become. Quantum mechanics, the science of the ultra-small, has rewritten the rules of reality, and when we apply those rules to the birth of the cosmos, things get wild. Was the universe always destined to be what it is, or did it flicker between countless possibilities before settling into existence? Could the very fabric of space-time have been in a quantum haze, a cosmic dice roll that somehow landed on our version of reality? These aren't just thought experiments, they're real theories from the edge of physics, and they might hold the key to understanding where everything came from. In this video, we're diving headfirst into 30 groundbreaking theories about the universe's first quantum superposition. From the idea that multiple universes branched out from that initial uncertainty to the possibility that time itself emerged from a quantum fog, we'll explore the most daring, brilliant, and downright bizarre ideas scientists have proposed. Some might sound like they're straight out of a fantasy novel, but they're backed by cutting-edge math and observations that could reshape everything we know. So buckle up, by the end of this journey, you might never look at the cosmos the same way again. Let's start with the first mind-bending idea, quantum fluctuations birthing the universe. Even in what we call empty space, the quantum vacuum is anything but empty. At unimaginably tiny scales, particles flicker in and out of existence, borrowing energy from nowhere and vanishing before reality can protest. This isn't magic, it's quantum field theory in action. Now, stretch that idea to the very beginning. What if the universe itself was one of those fluctuations? A cosmic roll of the dice where quantum uncertainty momentarily allowed everything to emerge from nothing. In this wild scenario, the first superposition wasn't just a particle being in two places at once. It was the entire cosmos existing, and not existing simultaneously. A Schrödinger's cat on the grandest scale imaginable. Only when this proto-universe collapsed out of superposition did it commit to being the reality we know. But here's where it gets even stranger. Some physicists suggest this quantum genesis didn't just happen once. If the vacuum can spawn one universe, why not countless others? Our cosmos might be a single bubble in a frothing quantum foam, where other universes flicker into being with entirely different laws of physics. This ties directly into the multiverse concept, where every possible quantum outcome becomes real somewhere. It's a staggering thought, the Milky Way, the laws of gravity, even the fact that you're watching this right now, might all stem from a single quantum fluctuation that got lucky. Now shift gears to an even more radical idea, the holographic universe. Imagine reality as a projection, like a three-dimensional movie encoded on a flat surface. The holographic principle suggests our universe's entire history, every star, every thought, every law of physics, might be the shadow of quantum information smeared across a distant two-dimensional boundary. In this theory, the first superposition wasn't in our familiar three dimensions at all. Instead, it happened outside space-time, on that elusive boundary where quantum bits danced in chaotic possibility before resolving into the code that generated everything. String theorists love this idea because it could unify gravity with quantum mechanics, two forces that stubbornly refuse to play nice in conventional models. Think of it like a cosmic DVD. The movie you experience, planets, galaxies, your morning coffee, isn't stored in the scenes themselves, but in microscopic pits on the disk's surface. Similarly, the holographic universe implies that our vivid, three-dimensional reality is just the playback of quantum data written somewhere else. If true, the first moment of existence wasn't a big bang but a quantum computer booting up with superposition as its loading screen. Now let's crank the strangeness up a notch. What if the Big Bang wasn't just the birth of our universe, but the moment reality itself split? This is the idea behind multiverse branching at time zero, a theory so bold it reimagines the very first instant of existence as a cosmic fork in the road. Picture Schrödinger's cat, that famous thought experiment where a quantum particle's fate leaves the cat both alive and dead until someone opens the box. Now replace the cat with the entire universe. In this scenario, the moment of creation wasn't a single explosion. It was a quantum dice toss where every possible outcome actually happened, spawning infinite parallel realities in one dizzying instant. Think of it like a cosmic lightning strike fracturing into countless branches. The initial superposition, a quantum haze of all possible universes, suddenly decohered, collapsing not into one reality but all of them simultaneously. One branch became our universe with its specific laws of physics and constants fine-tuned for life. Another might have heavier gravity, making stars burn out in seconds. Another could have no stars at all. The math behind this isn't just speculative. It's rooted in quantum decoherence, the process that makes particles choose a state when observed. But here, the observer isn't a person, it's the universe itself, freezing its own quantum possibilities into concrete, unshakable timelines. This idea dovetails with Hugh Everett's many worlds interpretation, but with a twist. Instead of universes branching every time a quantum decision is made, they all started branching at the Big Bang. Imagine a tree with roots made of pure potential, where every trunk, branch, and leaf represents a universe with its own unique history. Somewhere in that labyrinth of realities, there's a version of you reading this script in a world where gravity is weaker, or pi equals exactly 3 absurdities that didn't make the cut in our cosmic lottery. Critics argue this theory turns science into untestable metaphysics, but proponents point to anomalies in the cosmic microwave background, ghostly imprints of the universe's infancy that could hint at collisions with other bubble universes. If true, the Big Bang wasn't a beginning. It was the first click of an infinite cosmic kaleidoscope, forever twisting into new configurations we'll never see. And that's just theory number 3. Buckle up, things are about to get even weirder. What if the universe needed a witness to exist? This isn't about ancient myths or divine creators. It's a radical idea buried in the math of quantum physics. The von Neumann-Wigner interpretation suggests something astonishing. The first quantum superposition of the universe didn't just collapse randomly. It took a conscious observer to shake potential into reality. Forget lab equipment or scientists in white coats. We're talking about a primordial consciousness, a fundamental awareness woven into the fabric of existence itself. Think back to the classic double-slit experiment, where particles act as waves until someone measures them, forcing them to choose a position. Now scale that up to cosmic proportions. If the early universe was a quantum haze of possibilities, what or who was the observer that made it snap into focus? Some theorists propose that consciousness isn't a latecomer to the universe but was there from the very beginning. A silent architect turning quantum noise into stars, galaxies, and eventually minds capable of wondering about it all. This idea dovetails with panpsychism, the view that consciousness is a fundamental property of matter, like mass or charge. In this framework, even subatomic particles might possess a whisper of awareness, and the universe's first moment could have been a kind of cosmic awakening. Picture trillions of quantum possibilities deciding to coalesce because some form of proto-consciousness interacted with them. It's as if reality blinked awake when something, maybe the universe itself, finally looked. Critics dismiss this as metaphysics disguised as physics, arguing there's no mechanism for consciousness to influence quantum states. But proponents point to unexplained quirks in quantum experiments, like the observer effect, where particles seem to know when they're being watched. Could these hints suggest that awareness isn't just a product of the universe but a participant in its very creation? One wild implication: if consciousness shaped the early universe, it might still be shaping it now. Every thought, every observation could be subtly tweaking reality's quantum undercurrents. It's a head-spinning loop. The universe creates minds that then sustain the universe. Whether this idea is profound or preposterous, it forces us to confront an eerie possibility that the cosmos might not just contain consciousness, but in some deep way is consciousness playing an endless game of quantum peekaboo with itself. Imagine two cosmic blueprints emerging from the quantum void, not one universe, but a pair, inextricably linked from their very first moment. This is the daring premise of entangled creation twins, a theory suggesting our universe might have a hidden sibling born in the same quantum breath. Like identical twins sharing a single egg, these universes could have formed in a shared superposition, their fates forever intertwined by quantum entanglement, that eerie phenomenon where particles influence each other instantly, no matter the distance. Here's the twist: while our universe blossomed into the world we know, its twin might have taken a radically different path, lurking just beyond the edges of detection. Take entanglement's strangest quirk: change one particle's spin, and its partner instantly flips too, defying the speed of light. Now picture that on a cosmic scale. If two universes were entangled at birth, their fundamental constants, gravity, the speed of light, even the structure of atoms, might still mirror each other in subtle ways. Some theorists propose this could solve one of physics' biggest headaches: dark matter. What if the missing mass in our universe isn't some exotic particle, but the gravitational shadow of its entangled twin? Every galaxy in our cosmos might be tugging on invisible counterparts in a parallel reality, their mutual pull explaining why stars orbit faster than our math predicts. The implications for quantum gravity are even wilder. Einstein's relativity and quantum mechanics famously clash, but entangled twins could offer a bridge. If space-time in one universe is linked to its twin's quantum states, their interaction might create the glue that binds gravity to the quantum world. Picture two dancers moving in perfect, unseen harmony. Their steps might look random alone, but together they reveal a hidden choreography. Similarly, entangled universes could conspire to produce effects we've been attributing to mysterious forces like dark energy. But how would we ever detect a sibling universe? Clues might hide in the cosmic microwave background, the afterglow of the Big Bang. Odd asymmetries or cold spots in this radiation could be bruises from a gravitational handshake with our twin. Others suggest hunting for particles that inexplicably vanish, as if slipping through a quantum backdoor into the other universe, the most tantalizing possibility. That our twins' physics diverged so dramatically it became a dark, sterile realm, devoid of stars but teeming with exotic matter, a cosmic funhouse mirror reflecting our own existence. This isn't just theoretical poetry. Lab experiments with entangled particles prove quantum connections can survive astonishing conditions. If nature allows such bonds between tiny particles, why not between the fabric of realities themselves? The idea reshapes the very meaning of universe, not a solitary island of existence, but part of a quantum duo, forever whispering to each other across the multiverse's hidden dimensions. And if that's true, the next great cosmic discovery might not be a new particle or force, but the faint echo of our universe's first and only sibling. Let's wrestle with one of the most unsettling ideas in modern physics. What if the first conscious observer of the universe wasn't a cosmic deity or an alien intelligence, but a random, self-aware flicker of quantum noise? This is the Boltzmann brain paradox, a thought experiment that turns the origin of existence into a cosmic game of chance. The premise is simple yet staggering. In an infinite sea of quantum fluctuations, the odds suggest that a fully formed, self-aware mind could spontaneously assemble from the chaos, complete with false memories of an entire universe. Now stretch that idea to the beginning of everything. What if the first quantum superposition wasn't just a haze of particles but a fleeting moment of proto-consciousness, a Boltzmann brain that briefly observed itself into reality before dissipating back into the void? The paradox gets its name from Ludwig Boltzmann, the 19th century physicist who realized that in a universe governed by entropy, rare fluctuations can produce order from disorder. A cup of coffee cools down, but statistically, there's a tiny chance its molecules could randomly align to heat it up again. Scale that up, and over unfathomable eons, a fully functioning brain could theoretically coalesce from the quantum foam, complete with imagined sensory input. Apply this to cosmology, and the implications are dizzying. If the early universe was a quantum soup of possibilities, perhaps its first collapse into a concrete state wasn't triggered by a particle or a force, but by a phantom observer that existed just long enough to make reality real. Critics pounce on the thermodynamic absurdity. A Boltzmann brain would require such an astronomically unlikely alignment of particles that it's statistically more probable for our entire universe with its billions of galaxies to exist as is than for a single self-aware fluctuation to emerge. But here's where quantum refinements enter the picture. Recent theories suggest that in the high-energy chaos of the early universe, where the arrow of time hadn't yet hardened, superposition states might have been stabilized by quantum gravity effects. A primordial Boltzmann brain wouldn't need to last for more than a Planck instant, just long enough to measure the universe into being before dissolving. Some physicists take this even further, proposing that the universe we perceive might still be a Boltzmann hallucination, a momentary blip in an otherwise lifeless void, with all of history, from dinosaurs to distant galaxies, merely an elaborate false memory. It's a horrifying prospect, but it highlights a deep tension in our understanding of quantum mechanics and entropy. If reality hinges on observation, what observes the observer? The Boltzmann brain paradox isn't just a quirky thought experiment. It's a stress test for our theories of existence, forcing us to ask whether the universe needs a witness, or if the witness might be the universe's strangest accident. Yet there's a twist. New work in quantum information theory suggests a way out. If the early universe was a closed, self-referential quantum system, its initial superposition might have self-collapsed through internal entanglement, no phantom observer required. Think of it like a house of cards that stabilizes itself by the weight of its own structure. In this view, Boltzmann brains aren't creators of reality, but cosmic mayflies, brief glitches in a system already destined to become the universe we know. Whether you find this idea profound or preposterous, it forces a humbling realization. Our entire cosmic history might balance on a knife's edge between inevitability and absurd chance. And that's just the sixth theory. Wait until you hear what comes next. Here's a radical shift in perspective. What if the Big Bang wasn't the absolute beginning, but just a violent transition from a previous cosmic phase? Loop quantum cosmology, or LQC, offers precisely this mind-bending possibility. Unlike classical physics, where space and time stretch smoothly to infinity, LQC suggests the fabric of reality is woven from tiny, indivisible threads, quanta of space-time so small, 1 trillion of them could fit inside a single atom. Picture the early universe not as a fiery point of infinite density, but as a seething quantum foam where these space-time quanta flickered in and out of existence, caught in a cosmic superposition of possible geometries. At the heart of LQC lies the concept of spin networks, abstract webs of interconnected lines representing the quantum states of space itself. Before the Big Bang, these networks might have existed as a shimmering probability cloud, with every possible configuration of space-time overlapping simultaneously. Imagine a kaleidoscope constantly rearranging itself, where each twist produces a new potential universe. In this view, the singularity vanishes, replaced by a quantum bounce, a moment when gravitational repulsion from these space-time quanta reversed a collapsing predecessor universe into our expanding one. The math reveals something astonishing. As you rewind time, gravity doesn't spiral toward infinity. Instead, quantum effects create a wall of resistance, like a cosmic trampoline that stops space from crushing into nothingness. This means the Big Bang could have been the moment a superposition of spin networks finally chose a configuration, snapping into the space-time we recognize. Some versions of the theory even suggest traces of that pre-bang universe might linger in quantum correlations etched into the cosmic microwave background, ghostly fingerprints from a reality that once was. To grasp how wild this gets, think of space-time as a pixelated image. Zoom in far enough and the smooth picture breaks into discrete dots, except here, each pixel is a quantum of space vibrating between possible states. Before the Big Bang, these pixels weren't just uncertain, they were everywhere at once, like a cosmic game of quantum Tetris with all possible blocks hovering in place until gravity's rules snapped them into alignment. Critics argue LQC is untestable, but proponents point to potential signatures, subtle irregularities in the universe's expansion rate, or unexpected echoes in gravitational waves. If detected, these could hint at a quantum structure to space-time, proving the universe didn't emerge from nothing, but from a quantum storm of possibilities frozen into reality by the cold calculus of probability. This isn't just theory, it's a revolution in how we view existence. If LQC holds, the Big Bang becomes less a beginning and more a turning of the cosmic hourglass, with our universe merely the latest page in an infinite quantum story. And if that's true, the deepest question isn't how did it all start, but what came before the before? What if the universe didn't just begin? What if it programmed itself into existence? This is the spine-tingling premise of the simulation bootstrap theory, where the cosmos emerges not from a singularity or quantum fluctuation, but from a self-referential loop of computation. Imagine a cosmic version of a computer booting up, except the hardware and the software are the same thing: reality encoding itself into existence by performing calculations on its own quantum structure. At the heart of this idea lies a radical fusion of two concepts: self-simulation and quantum computing. In a traditional computer, information is processed using bits, zeros and ones. But quantum computers use qubits, which can exist in superpositions of states, performing countless calculations simultaneously. Now stretch that to the universe's first moments. If space-time itself has a quantum computational structure, as some theorists propose, then the Big Bang might not have been an explosion. It could have been the first cycle of a universe-scale quantum algorithm, a process where reality iteratively defined its own rules by computing them into being. Think of it like a snake eating its own tail, but with math. The universe's initial quantum superposition wasn't just a fog of possibilities. It was a program running on the fabric of existence, testing every possible configuration of physical laws until it found one stable enough to persist. This isn't just abstract philosophy. Scientists working on quantum gravity have found hints that space-time might fundamentally operate like a network of entangled qubits, with every particle interaction akin to a logical operation in some vast cosmic processor. Here's where it gets even wilder. If the universe is self-simulating, it wouldn't need an external programmer. Instead, its own quantum mechanics could act as the compiler, translating potential into reality through sheer computational inevitability. Picture a game of 20 questions where the universe is both the player and the answer, asking itself what it should be until the answers crystallize into the laws of physics we observe. Some versions of this theory suggest that dark energy, that mysterious force accelerating the universe's expansion, might actually be the computational overhead of reality constantly recalculating itself. Critics argue this veers into metaphysics, but proponents point to concrete parallels. Quantum error correction, a technique used in real-world quantum computers, bears eerie similarities to how space-time seems to smooth out microscopic fluctuations into the orderly universe we see. And if the universe is fundamentally computational, it might explain why math describes reality so unnervingly well, because reality is math executing itself at the Planck scale. The most mind-bending implication: if the universe bootstrapped itself via quantum computation, we might be living inside a simulation, not one run by aliens in a higher reality, but a self-contained loop where existence is both the simulation and the simulator. It's a cosmic Ouroboros where the beginning and the end are the same line of code. And if that's true, the deepest mysteries of physics, from the nature of time to the origin of consciousness, might not be features of the universe, but bugs waiting for reality's next update. Now let's turn reality inside out with a theory so counterintuitive it makes time itself dizzy. What if the universe's first quantum superposition wasn't just a choice between different physical states, but a collision between time flowing forward and backward simultaneously? This is the spine-chilling premise of the time-reversed universe hypothesis, where the Big Bang birthed not one arrow of time but two, locked in a quantum embrace before violently splitting apart. At the heart of this idea lies a fundamental symmetry in physics called CPT charge parity and time reversal. The laws of nature, remarkably, stay almost identical if you flip a particle's charge, mirror its position, and run the clock backward. But here's the kicker: while small particles obey this symmetry, the universe as a whole doesn't. Time flows relentlessly forward, eggs don't unscramble themselves, and coffee never unstains your shirt. So what broke the symmetry? The answer might lurk in the universe's first quantum state, a moment when time hadn't yet chosen its direction. Picture this: a primordial superposition where two universes coexisted, one evolving forward from the Big Bang, the other backward toward it, like a cosmic palindrome. In this fragile state, entropy could have flowed both ways, with quantum probabilities perfectly balanced. Then, as decoherence kicked in, the superposition collapsed, leaving us with the forward-flowing timeline we experience, while the backward universe might still exist, forever hidden behind the veil of our perception. This isn't just speculative math. Recent experiments in quantum optics have shown particles behaving as if influenced by future events, a phenomenon called retrocausality. In one groundbreaking study, scientists demonstrated that measurements made on a photon after it traveled through a maze seemed to affect its path before the measurement occurred. It's as if quantum particles occasionally cheat causality's rules, hinting that time's arrow might not be as rigid as we thought. Now scale that up to cosmic proportions. If microscopic particles can blur the line between past and future, why couldn't the infant universe? Some models suggest the Big Bang's fireball contained equal parts matter and antimatter, a perfect CPT mirror image, until a quantum instability tilted the scales. That tiny bias might have frozen time's arrow into the forward flow we know, while the other half of the superposition became a ghost universe where stars form from dust clouds coalescing out of supernovas and light travels back into flashbulbs. The wildest implication: this theory could solve one of cosmology's greatest puzzles: why our universe appears so finely tuned for life. If time-symmetric superpositions naturally explore all possible configurations before selecting one, ours might have been chosen precisely because it allowed complexity to emerge. Meanwhile, the time-reversed twin could be a barren wasteland where structure crumbles into chaos, a cosmic photo negative fading into the quantum background. Critics argue this stretches quantum weirdness beyond plausibility, but proponents point to eerie patterns in cosmic voids and the universe's unexpected large-scale uniformity. Could these be echoes of a time-symmetric beginning where two cosmic destinies briefly overlapped before unraveling? Whether this idea holds or not, it forces us to confront a humbling truth. The flow of time we take for granted might just be the path of least resistance in a far stranger multiverse, one where every beginning is also an end, and the first quantum dice roll landed on now. Imagine a cosmic version of survival of the fittest, not for life, but for the very laws of physics themselves. This is the startling proposition of quantum Darwinism, a theory suggesting our universe's classical, predictable behavior wasn't guaranteed at the outset. Instead, it might have been selected from a quantum smorgasbord of possibilities through a relentless process of environmental interaction. At the microscopic scale, quantum Darwinism explains why we don't see cats both dead and alive in our everyday lives. When a quantum system interacts with its environment, whether through photons bouncing off it or air molecules colliding with it, countless tiny measurements occur, reinforcing certain states while erasing others. Over time, only the most stable, reproducible states survive this decoherence, becoming the classical reality we perceive. Now, stretch this idea to the birth of the cosmos. If the early universe existed in a superposition of possible configurations, different laws, different constants, even different dimensions, then its environment wasn't just empty space. It was a seething quantum foam, a chaotic soup of gravitational waves, particle-antiparticle pairs, and fluctuations in the very fabric of space-time. In this primordial arena, certain universe configurations would have been more fit than others. A cosmos with wildly unstable gravity might have collapsed instantly. One with no electromagnetism would lack stars or planets. But a universe like ours, with just the right balance of forces to allow structures to form and persist, would have been repeatedly measured and reinforced by its own evolving environment. Think of it like a cosmic game of telephone, where only the clearest, most stable messages get passed along through the noise of quantum interactions. Over Planck time scales, this process could have pruned away the vast majority of quantum possibilities, leaving behind the familiar, classical universe we see today. The eerie parallel to biological evolution is no accident. Just as natural selection filters random mutations for traits that enhance survival, quantum Darwinism filters quantum states for those resilient enough to withstand environmental scrutiny. The key difference: instead of competing for resources, universe-scale quantum states competed for stability. Constants like the speed of light or the strength of gravity might not be fundamental truths, but the winners of a decoherence marathon that began 13.8 billion years ago. Critics argue this merely shifts the mystery from why these laws to why this selection process, but proponents point to tangible evidence: the universe's startling uniformity. The cosmic microwave background shows a near-perfect equilibrium, as if the cosmos has been averaged out by countless quantum interactions. Even more provocative, some interpretations suggest dark matter and dark energy could be relics of this selection process, quantum states that almost decohere but still whisper at the edges of reality. The boldest implication: if quantum Darwinism shaped our universe, others might have stabilized into radically different forms. Some could be ghostly realms where gravity leaks into extra dimensions. Others might be frozen wastelands where time never fully clicked into alignment. Our universe isn't special, just statistically inevitable, like a six-sided die landing on 3 enough times to convince us it's the only possible outcome. This reframes the fine-tuning problem entirely. Instead of asking why the universe is perfectly suited for life, we might ask, how many quantum branches had to collapse before one produced observers capable of asking the question? The answer could lie not in a designer's blueprint, but in the relentless, impersonal sieve of quantum decoherence, a cosmic filter that turned possibility into reality, one interaction at a time. Take everything you know about black holes, those cosmic vacuum cleaners where gravity wins forever, and flip it inside out, literally. A white hole is its theoretical opposite, a region of space where matter and energy can only pour out like a cosmic fountain with no off switch. Now imagine these two extreme objects weren't separate at all, but connected through a quantum tunnel where the rules of cause and effect get blurry. This is the black hole-white hole bridge hypothesis, a theory so audacious it suggests our entire universe might be the aftermath of one of these cosmic shortcuts snapping into existence. At the heart of this idea lies a radical reimagining of the Big Bang. Instead of a singularity, a point of infinite density where physics breaks down the universe's birth could have been a quantum transition. Picture a supermassive black hole in some other reality, collapsing not into oblivion but into a quantum superposition where its crushing gravity and a white hole's explosive repulsion existed simultaneously. For a fleeting instant, this bridge would balance on the knife's edge of physics, neither fully collapsing nor exploding, but hovering in a state of pure potential. Then, like a cosmic coin toss landing on its edge, the superposition collapses and reality chooses the white hole side, birthing our expanding universe in a fireball of pent-up energy. Recent breakthroughs in loop quantum gravity lend eerie credibility to this idea. The math suggests black holes don't necessarily end in singularities, but could rebound into white holes through quantum effects. Imagine squeezing a spring to its limit just when it seems it can't compress further. It recoils with pent-up force. Similarly, a black hole's collapse might hit a quantum bounce point where space-time's granular nature prevents infinite density, triggering a reversal into expansion. Some calculations even show this transition could happen fast enough, in mere milliseconds from an outside viewer's perspective, while appearing to take billions of years for someone falling into the black hole. This time-warping effect could explain why we perceive our universe as ancient, even if it began as a sudden quantum flip. But here's where it gets stranger. If our universe emerged from such a bridge, traces of its origins might linger in the cosmic microwave background. Certain anomalies, like unexpected cold spots or spiral patterns in this primordial radiation, could be echoes of the white hole's initial outburst. Even more provocative, this model might solve the mystery of why our universe appears so finely tuned. The quantum bounce wouldn't be random, but filtered by the black hole's previous structure, like a cosmic photocopier preserving only the most stable physical constants from the parent reality. Critics argue such bridges would require exotic negative energy or violate entropy, but proponents counter with quantum tunneling, the same phenomenon that lets particles cheat through barriers in labs. On a cosmic scale, the entire universe might have tunneled out of a black hole's corpse. It's a staggering thought. Every galaxy, every atom, might owe its existence to a quantum Houdini act where reality escaped gravity's trap by rewriting the rules. The implications ripple outward. If black holes birth universes, our own might contain cosmic wombs where new realities are constantly budding into existence, invisible inside event horizons. The multiverse wouldn't just branch through time, it could be a fractal cascade of black hole births, each carrying forward tweaked versions of physics. We might even be living inside someone else's discarded singularity, our Big Bang another universe's collapse in disguise. Whether this theory holds or not, it forces us to confront a humbling possibility. The universe might not have started from nothing, but from everything somewhere else, a quantum heir to a reality we'll never see. What if mathematics isn't just a language we invented to describe reality, but reality itself? This is the spine-tingling core of Max Tegmark's mathematical universe hypothesis, where numbers, equations, and geometric structures aren't tools for understanding existence, they are existence. Picture the early universe not as a soup of particles or energy, but as an infinite tapestry of pure mathematical possibility. Every conceivable structure, from the simplest geometric shapes to hyper-complex equations governing alien physics, existed simultaneously in a quantum superposition, a cosmic library where every book was equally real until one was plucked from the shelves. Tegmark's idea reframes the multiverse in startling terms. Instead of parallel worlds branching from quantum choices, the mathematical universe suggests every self-consistent mathematical structure already exists as a standalone reality. Our cosmos, with its 3 spatial dimensions and particular physical constants, is just one page in an unimaginably vast catalogue. Here's where it gets quantum. The instant before the Big Bang might have been a superposition of all possible mathematical universes, with decoherence collapsing the system into the specific structure we now inhabit. Imagine flipping through a notebook where every page sketches a different universe, some with fractal time, others with 26 dimensions, and suddenly the ink on one page darkens into 3-dimensional solidity while the rest fade into potentiality. The implications rewrite how we classify multiverses. Traditional taxonomies sort parallel realities by how they branch: quantum splits, inflationary bubbles, or higher dimensional membranes. But in Tegmark's framework, multiverses are sorted by mathematical type. Level 1 contains variations of our own physics' cosmic cousins where atoms spin slightly faster or gravity is weaker. Level 2 introduces entirely new constants, like universes where pi equals 4 or light speed isn't constant. Level 3, realities built on equations we haven't even discovered yet, where space-time has no meaning and causality runs backward. The hierarchy climbs until level 4, where all mathematical structures exist, even those incompatible with observers like us. This leads to an eerie corollary. The so-called fine-tuning of our universe might be an illusion. If every possible math structure exists, it's statistically inevitable that some would produce conditions for life, no divine hand required. Think of it like rolling a million-sided die. Of course, one result will look improbably perfect. Worse yet, some versions of Tegmark's theory suggest conscious observers might drag their preferred mathematical framework into existence, a cosmic twist on the observer effect where minds don't just collapse quantum states, they collapse entire logical systems into reality. Critics pounce on 2 flaws. First, how does a purely mathematical universe feel like anything? Why do we experience the taste of coffee or the color red if reality is just equations? Tegmark counters that consciousness itself could be a mathematical pattern, an inevitable byproduct of certain information processing structures. Second, there's the problem of testability. If a level 4 multiverse contains every possible structure, it risks explaining nothing by explaining everything, yet supporters point to glimmers of hope. If our universe's math is simple compared to alternatives using the fewest axioms to generate richness, that simplicity might leave detectable fingerprints in the cosmic microwave background or quantum entanglement patterns. The most haunting implication: if Tegmark is right, Pythagoras wasn't just a philosopher, he was a prophet. Numbers might not describe the universe's music, they might be the music playing across infinite dimensions we'll never hear. And somewhere in that grand symphony, there's a universe where 2 + 2 = 5, humming quietly in the dark. Picture space-time not as an empty stage where the universe plays out, but as something far stranger, a frothing quantum sea that only looks smooth from a distance. This is the essence of the quantum gravity phase transition theory, where the familiar fabric of reality might have crystallized out of a swirling, structureless medium like ice forming on a turbulent lake. At ultra-small scales, trillions of times tinier than an atom, our classical notions of space and time may completely break down. In this primordial quantum foam, gravity wouldn't yet behave like the force we know. Instead, it might have been an emergent property of something deeper, a seething network of entangled quantum interactions where concepts like here and now had no meaning. The transition to classical space-time could have been as dramatic as water freezing, an abrupt shift from liquid chaos to structured solidity. Superfluid vacuum theory offers a striking analogy. In a superfluid, particles lose all friction and move in perfect unison. creating bizarre behaviors like climbing walls or forming vortexes that never dissipate. Now imagine the vacuum of space itself as a superfluid, a frictionless medium where quantum fluctuations aren't defects but the fundamental substance. Before the Big Bang, this medium might have existed in a high-energy, disordered state, with space and time dissolving into a formless quantum turbulence. Then, as the universe cooled past a critical threshold, space-time condensed into the orderly grid we recognize, much like steam cooling into water droplets. The math behind this is mind-bending. Certain quantum gravity models suggest that what we perceive as three-dimensional space could be a holographic projection from a two-dimensional boundary, the way ripples on a pond's surface hint at unseen depths. In this view, the cosmic phase transition wasn't just about temperature, it was about information suddenly organizing itself into stable patterns. The very geometry of space-time might have emerged from quantum entanglement, with particles becoming correlated across vast distances to stitch together the fabric of reality. Evidence could lurk in the cosmic microwave background's faintest whispers. If space-time crystallized unevenly during this transition, microscopic cracks might have formed, cosmic defects similar to cracks in freezing ice. These imperfections could have left faint imprints on the universe's oldest light, detectable as peculiar hot or cold spots in the radiation bathing our skies. Even more tantalizing, gravitational wave observatories might eventually catch echoes of the transition itself, ripples in space-time carrying fingerprints from the moment gravity switched on as a distinct force. The implications rewrite our cosmic origin story. The Big Bang wouldn't mark the absolute beginning, but the moment quantum gravity's chaos first settled into recognizable order. It's as if reality spent its earliest moments tuning an instrument, endless discordant notes collapsing into a single chord that became the soundtrack of the universe. And if that's true, the deepest question isn't what came before the Big Bang, but what symphony might still be playing just beyond the edges of our perception. The universe might not just run like a computer. It could be one processing its own existence into being through sheer quantum computation. This is the audacious claim of the conscious quantum code theory, where reality's first moments weren't governed by particles or forces, but by self-referential information loops dancing in superposition. Imagine an algorithm that writes itself as it executes, each line of code generating the rules for the next, except here, the program is space-time itself, and the output is everything that ever existed. At the core of this idea lies quantum information theory, which treats reality as a network of entangled qubits constantly performing operations. In the beginning, these qubits wouldn't have represented particles or energy, just raw, abstract potential. Like a cosmic game of 20 questions where the universe asks itself, "What am I?" over and over, each quantum operation narrowing the possibilities until reality crystallized. Some physicists suggest this process might have been guided by a primitive form of proto-consciousness, not as a ghost in the machine, but as an intrinsic property of information integration. This ties directly to integrated information theory, or IIT, which proposes that consciousness arises when a system reaches a critical threshold of interconnected computation. Apply that to the infant cosmos, and the first quantum superposition could have been the universe thinking itself into existence. The parallels to quantum cognition are eerie. Just as human decision-making might harness quantum processes like superpositioned mental states collapsing into choices, the early universe could have performed a similar trick on a cosmic scale. Picture a cosmic version of the double-slit experiment, where reality behaves as both wave and particle until observed. Except in this case, the observer isn't a scientist, it's the universe's own growing complexity, acting as its own measurement device. Every quantum fluctuation, every entanglement becomes a step in the universe's bootstrap operation, pulling itself up by its own informational bootstraps. Supporters point to startling evidence in the fabric of space-time, the universe's holographic nature, where a two-dimensional surface can encode three-dimensional reality, mirrors how quantum computers correct errors by distributing information across entangled qubits. Even dark energy's mysterious acceleration could be a side effect of the cosmic processor constantly allocating more memory to sustain reality's expanding complexity. And if the universe truly emerged from self-processing information, it might explain why math describes physics so unnervingly well, because math isn't just the language of reality, it's the substrate. Critics argue this veers into panpsychism, the idea that consciousness is fundamental, but proponents counter with cold, hard computation. In lab experiments, even simple quantum systems exhibit primitive decision-making behaviors, optimizing states in ways that resemble learning. Scale that up to universe-sized quantum networks, and the line between physics and cognition blurs. After all, if a single neuron firing feels like nothing, but a trillion interconnected neurons create subjective experience, why couldn't a sufficiently complex quantum system birth its own kind of cosmic awareness? The most radical implication: if the universe runs on conscious quantum code, we might not just be inhabitants of reality, we could be participants in its ongoing computation. Every observation, every measurement might subtly tweak the cosmic algorithm, like cells in a brain collectively shaping the mind they inhabit. It's a dizzying loop. The universe computes itself into existence, spawns minds that observe it, and those observations in turn refine the computation. The Big Bang wasn't an explosion, it was the first thought in a cosmic dream that's still unfolding. Imagine a single quantum hiccup so small, so fleeting that it spawned an endless cascade of universes. This is the staggering premise of the eternal inflation seed theory, where the cosmos didn't just burst into being, but sneezed into an infinite fractal of realities. At the heart of this idea lies a quantum twist on inflation, the period when the universe expanded faster than light in its first sliver of a second. But here's where it gets wild. Inflation might not have been a one-time event triggered by classical physics. Instead, it could have been sparked by a quantum superposition of vacuum states, like a cosmic roulette wheel landing on every number at once, each spin birthing a new universe. Picture the primordial quantum foam not as empty space, but as a seething ocean of potential energy levels. Some pockets of this foam would have existed in high-energy false vacuums, teetering on the edge of stability. Others hovered in lower energy states closer to equilibrium. Now, imagine these vacuum states weren't fixed, but existed in superposition, an undulating quantum wave of possibilities where every energy configuration was simultaneously real. When this superposition finally collapsed, it wouldn't have settled into a single vacuum state. Instead, quantum fluctuations could have locked in inflation eternally, with high-energy bubbles continuously nucleating new universes like bubbles in a boiling pot that never runs dry. The mechanics are stranger than fiction. In this scenario, our entire observable universe might be just one bubble in an ever-expanding quantum foam of inflating regions. Each bubble universe would have crystallized out of the false vacuum with its own random physical constants, some with gravity too weak for stars, others with electromagnetism so strong atoms couldn't form. The mind-bending part: this process never stops. Even now, beyond the edge of our cosmic horizon, new bubble universes could be sprouting from quantum fluctuations in the eternally inflating background, their births unobservable but mathematically inevitable. This leads to the notorious measure problem. How do you calculate probabilities in an infinite multiverse where every possible outcome happens somewhere? If inflation truly is eternal, there are infinitely many versions of you reading infinitely many variations of this script. Somewhere, a universe exists where gravity repels and time flows in zigzags. So why does our universe seem so improbably fine-tuned? Physicists wrestle with nightmarish math to weigh these possibilities, debating whether bubble universes closer to the quantum seed are more real than latecomers, or if consciousness somehow biases our observations. Clues might hide in the large-scale structure of our cosmos. If our bubble universe collided with others during inflation, the bruises could linger in the cosmic microwave background as anomalous cold spots or strange rotational patterns. Some models even suggest dark energy, the mysterious force accelerating the universe's expansion, could be a remnant of our bubble's quantum decoupling from the inflating background, like a fading echo of the first superposition's collapse. The most humbling implication: if eternal inflation is true, the Big Bang wasn't the absolute beginning, just a local event in an unending quantum cascade. Our entire reality might be a fleeting fluctuation in an endless meta-universe where creation never stops, and every quantum maybe begets another layer of the multiverse. It's not just that the universe had a quantum beginning, it might still be quantum birthing more universe right now, forever. What if the universe didn't just happen to be perfect for life, but required observers to crystallize into existence at all? This is the quantum anthropic principle, a theory so radical it places consciousness at the center of cosmic creation. Forget the idea of a random universe accidentally conducive to life. This framework suggests the first quantum superposition contained every possible universe, with observers like us acting as cosmic gardeners, pruning the infinite branches until only one reality remained. At its core, this principle reimagines the fine-tuning problem, the eerie precision of constants like gravity and electromagnetism that allow stars, planets, and life to exist. In classical physics, these values seem astronomically improbable, as if someone dialed them in deliberately. But the quantum anthropic view flips the script. The constants aren't fine-tuned for us, we're the ones who did the tuning. Picture the early universe as a quantum kaleidoscope, shimmering with countless configurations, some with gravity too weak for galaxies, others with chemistry too chaotic for DNA. Most of these branches would have been dead ends, collapsing immediately into oblivion. But one path, the one where particles align just right to eventually form conscious observers, stabilized through sheer act of being perceived. The mechanism mirrors quantum decoherence in labs. When a particle exists in superposition, interaction with its environment forces it to choose a state. But here, the environment isn't just detectors or dust, it's the potential for future observation woven into the fabric of reality itself. If a universe's quantum state couldn't sustain observers, it decohered into nothingness. Only observer-compatible branches survived the collapse, making it seem like the universe was fine-tuned when in truth, we're leftovers from a quantum selection process. This idea gains teeth when applied to multiverse theories. In the many worlds interpretation, every quantum decision spawns parallel realities, but the quantum anthropic principle adds a filter. Only worlds that can be observed persist, while others fade like unread books in a library. Some versions of the theory take this further, suggesting conscious observation doesn't just select universes, it generates them. Imagine planting a tree by looking at its shadow. In this view, the Big Bang's quantum haze only solidified into stars and planets because future minds measured it into being through the retroactive weight of observation. Critics argue this skirts solipsism, but proponents point to quantum experiments like delayed choice tests, where particles seem to decide their behavior based on future measurements. If a photon can retroactively adjust its path because it will be observed, why couldn't the universe do the same on a grand scale? Even the cosmic microwave background's unexpected smoothness could hint at this, a fingerprint of quantum branches where only the most stable, life-friendly configurations survived decoherence. The implications shatter conventional cosmology. If consciousness plays an active role in shaping reality, the distinction between observer and observed blurs. We're not just bystanders in the universe, we're participants in its very construction, living in a world that exists because we're here to see it. Whether this idea is profound or paradoxical, it forces a humbling question. Did the universe create us, or did we, through the quantum weight of our attention, create it? Think of the universe's birth not as a smooth, continuous event, but as a frenzied, pixelated dance at the smallest possible scale. This is the holographic quantum foam theory, where space-time itself emerges from a seething ocean of Planck-scale pixels, flickering in and out of existence like static on an old TV screen. At these unimaginably tiny scales, the fabric of reality isn't a blank canvas, it's a frothing chaos of quantum fluctuations, where every pixel of space-time exists in superposition, churning with potential until the right conditions lock them into place. Now here's where the holographic twist comes in. Just as a 3D hologram is encoded on a flat 2D surface, the universe's information might not live in the three-dimensional space we experience, but on a distant, two-dimensional boundary we can't see. Picture a cosmic version of a movie projected from the edges of reality, except the projector isn't a machine, but the quantum foam itself, processing information into the illusion of depth, time, and even gravity. In this view, the Big Bang wasn't an explosion of matter. It was the moment this holographic code booted up, translating quantum chaos into the structured universe we recognize. The mechanics get even wilder when you consider how these space-time pixels behave. At the Planck scale, where distances are a trillion times smaller than an atom, quantum foam isn't just empty space. It's a turbulent sea of virtual particles, wormholes, and microscopic black holes popping in and out of existence so fast they defy classical physics. Some theories suggest these fluctuations aren't random noise, but bits of information constantly rewriting themselves, like a cosmic computer updating its code in real time. And just as a computer's binary code underpins complex software, these Planck-scale interactions might generate everything from galaxies to the sensation of time flowing forward. Evidence for this idea lurks in black holes, those cosmic traps where space-time bends into oblivion. When matter falls into a black hole, its information doesn't vanish but gets smeared across the event horizon, the point of no return. This aligns eerily with the holographic principle. The 3D information of the infalling matter is preserved on the 2D surface, like a cosmic thumb drive storing data in the thinnest possible layer. If black holes obey this rule, why wouldn't the universe itself? The most mind-bending implication. If the holographic foam theory is correct, our perception of a smooth, continuous universe is an illusion, a high-resolution approximation of reality's grainy quantum foundation. Zoom in far enough, and you'd find space-time isn't a fabric but a mosaic of discrete tiles, each one a pixel in the grand cosmic hologram. And if that's true, the Big Bang wasn't the beginning. It was just the moment the universe's quantum processor finally rendered a stable image. This might also explain why gravity feels so weak compared to other forces. In a holographic universe, gravity isn't a fundamental force, it's an emergent property, a side effect of information being projected from the boundary. Imagine blowing up a balloon with a grid drawn on it. From a distance, the grid looks smooth, but up close, you see the gaps between lines. Similarly, gravity's faintness could be a clue that we're sensing the gaps in space-time's underlying code, hints of a deeper, pixelated reality. For skeptics, the theory raises tough questions. How do we test something happening at scales a billion times smaller than we can probe? Yet supporters point to subtle fingerprints, anomalies in high-energy particle collisions, unexpected patterns in cosmic microwave background radiation, or even irregularities in gravitational waves. Each could be a flicker of the quantum foam beneath our feet, a reminder that the universe's smooth exterior hides a storm of information beneath. Whether this idea holds or not, it reshapes our cosmic origin story. The universe might not have begun with a bang, but with a hum. The sound of uncountable Planck-scale pixels booting up, rendering reality one quantum calculation at a time. And if that's the case, the deepest mysteries of existence, dark energy, the arrow of time, even consciousness itself, might not be features of the universe but glitches in the code waiting to be debugged. The universe might not have started with smooth, continuous space-time, but as a tangled web of pure connections, like a cosmic game of join the dots gone wild. This is the quantum gravity model, an idea so radical it suggests early reality resembled a frenzied scribble where every point connected to every other point simultaneously. Picture a hyperactive child's drawing where lines crisscross in every direction, linking stars to atoms to galaxies in one chaotic mesh, except here, the child was the universe itself, and the drawing wasn't on paper but etched into the fabric of existence. In this model's earliest phase, space-time didn't exist as we know it. Instead, a seething quantum graph dominated, an abstract network where every node was connected to every other node with equal strength, creating a state of perfect symmetry. Energy blazed so intensely that distinctions like here and there held no meaning. Distances fluctuated wildly. 2 points could be neighbors or light years apart depending on how the quantum connections vibrated. This was reality in its rawest form, pure relational potential, a cosmic subway map with all stations linked by express lines and no passengers. Then came the critical shift. As the universe cooled, this ultra-connected graph underwent a phase transition like water freezing into ice where most connections severed, leaving behind a sparse lattice akin to our familiar space-time. The hot, high-energy state, where every quantum node chattered with every other, gave way to a cold, low-energy arrangement where only nearby nodes remained linked. Suddenly, locality emerged. Points far apart in the graph became distant in space, while nearby points defined local geometry. The tangled scribble smoothed into cosmic graph paper, with gravity arising naturally from the leftover connections' tension, like cosmic rubber bands pulling matter along the lattice's grid lines. Recent lattice quantum gravity simulations bring this idea to life. Supercomputers modeling these graphs show something astonishing. When the connection strength drops below a critical threshold, the system spontaneously generates 4-dimensional space-time, 3 dimensions of space, 1 of time, matching our universe's structure. Even Einstein's equations emerge naturally from the graph's dynamics, suggesting gravity might not be a fundamental force, but a side effect of information flowing through this cosmic network. It's as if the universe booted up like a computer game, starting with maximum settings before optimizing itself into the sparse, efficient world we inhabit. The most startling evidence, this model could explain dark energy, the mysterious force accelerating cosmic expansion. In quantum gravity's framework, the vacuum energy driving this acceleration might be residual tension from severed high-energy connections, like phantom limbs of the universe's hyperconnected youth. Even the speed of light finds new meaning. It becomes the maximum rate information can hop between nodes in the lattice, putting a cosmic speed limit on causality itself. Critics argue the theory is too abstract, but proponents point to real-world analogues. Graphene, a material just 1 atom thick, exhibits bizarre quantum behaviors because its carbon atoms arrange in a hexagonal lattice, a microscopic cousin of quantum gravity's cosmic web. When electrons zip through graphene, they mimic particles navigating emergent space-time, hinting that nature might favor such relational structures at all scales. If this model holds, the Big Bang wasn't an explosion, it was a cosmic simplification, a shedding of infinite connections to reveal the clean geometry beneath. The universe's first quantum superposition wasn't of positions or energies, but of possible graphs, each a blueprint for a different kind of reality. And somewhere in that labyrinth of links, our particular lattice won out, trading chaos for the elegant structure we now call home. The universe's first quantum state might not have been a singular event, but an infinite hall of mirrors repeating the same patterns at every conceivable scale. This is the essence of the self-similar quantum fractal theory, where the Big Bang superposition wasn't confined to a single moment or size. Instead, it rippled across all dimensions, from the Planck scale to the cosmic horizon, weaving reality into a tapestry where every thread echoed the same fundamental design. Imagine zooming into a snowflake's edge only to find the same intricate branches repeating endlessly, except here, the snowflake is space-time itself, and the patterns aren't frozen but alive with quantum possibility. This idea finds startling support in renormalization group flow, a mathematical tool physicists use to study how quantum systems behave at different scales. Normally, particles and forces appear distinct depending on how closely you examine them, like how water seems smooth from a distance but dissolves into chaotic molecules up close. But renormalization reveals hidden symmetries. Zoom in or out far enough, and certain systems begin to look eerily similar. Apply this to the universe's infancy, and a radical picture emerges. The first quantum superposition might have been scale invariant, a fractal fluctuation where the same quantum dances played out in the behavior of quarks, galaxies, and everything in between. It's as if the universe booted up not with a single equation but with a single theme repeated across an infinite spectrum. The implications rewrite how we view cosmic structure. Take galaxy clusters. From afar, their distribution mirrors the atomic lattice of a crystal. Even the cosmic microwave backgrounds, fluctuations, the universe's baby picture, show patterns statistically identical whether you analyze them in patches the size of a city or a continent. Could these echoes be remnants of that primordial fractal superposition? Some models suggest yes, that the universe's first quantum state wasn't just a haze of particles, but a nested set of probabilities, each layer a scaled-up or scaled-down version of the last. Here's where it gets even stranger. In quantum field theory, renormalization isn't just a trick, it's a necessity. Calculations often spit out infinities when probing tiny scales, forcing physicists to renormalize their equations by effectively subtracting infinite terms. But what if these infinities aren't mathematical nuisances but clues? The self-similar fractal theory posits that these divergences hint at a deeper truth. The universe's fundamental structure has no preferred scale. The same quantum rules governing electron spins might once have dictated the spin of galaxy clusters, locked in a cosmic resonance now frozen into the fabric of space-time. Critics argue this risks circular reasoning finding patterns because we're primed to see them, yet proponents point to concrete phenomena. Turbulence in fluids, earthquake distributions, even the branching of neurons in your brain, all exhibit fractal behavior emerging from simple rules iterated across scales. If nature favors these patterns everywhere, why not at the universe's birth? Even black holes, those cosmic vacuum cleaners, might preserve fractal signatures in their event horizons, with microscopic quantum jitters echoing the gravitational waves from colliding behemoths. The most profound implication: if the universe's first superposition was truly fractal, then every star, every atom, might carry a faint whisper of that original quantum symmetry, a cosmic inheritance written into the very code of reality. It's not just that the universe has patterns, it might be a pattern endlessly unfolding with the Big Bang as the first brushstroke in an infinite recursion. And if that's true, the search for a theory of everything might not be about finding new laws, but recognizing the old ones repeating themselves at every scale, waiting to be decoded. Quantum Darwinism doesn't just shape particles, it might have sculpted the universe itself, using cosmic horizons as chisels to carve reality from quantum chaos. Picture the early universe not as a smooth continuum, but as a storm of probabilities where every possible configuration of space-time flickered in and out of existence. In this quantum whirlwind, how did the crisp, classical universe we know emerge? The answer could lie in the universe's own horizon's boundaries, like the edge of observable space or the veil around black holes acting as unintentional observers. forcing quantum possibilities to collapse into tangible reality through countless subtle interactions. Consider the cosmic microwave background, the afterglow of the Big Bang. Its eerie uniformity suggests something erased the quantum roughness of the early universe, smoothing it into the orderly cosmos we see. Quantum Darwinism offers a mechanism. Photons traveling across the infant universe interacted relentlessly with their environment, their quantum states decohering into classical certainty as they bumped into particles. Every collision, every scattering event was a tiny observation, reinforcing stable configurations while quantum noise faded into oblivion. Over billions of years, this process didn't just happen to photons, it happened to space-time itself, with cosmological horizons playing the role of a cosmic audience, eternally measuring the universe into coherence. The event horizon of a black hole provides a stunning example. As particles approach this boundary, their quantum information gets smeared across it in a process called holographic encoding. In essence, the horizon observes and records the particle states, freezing them into classical existence, now scale that up to the universe's infancy. The Hubble horizon, the limit of how far light could travel in the early cosmos, might have functioned similarly, acting as a quantum filter that amplified certain space-time configurations while suppressing others. The result, a universe that looks classical not because quantum physics breaks down at large scales, but because the system's own boundaries tirelessly perform trillion upon trillion of quantum measurements, each one pruning the tree of possibilities until only the most stable branches remain. This idea reshapes how we think about the arrow of time. Entropy increases because quantum Darwinism favors states that can be replicated and shared, like a cosmic game of telephone where only the clearest messages survive. The past appears fixed because those quantum states were relentlessly observed by their environment, while the future remains fluid, a superposition yet to be collapsed by the universe's ceaseless computation. Even dark energy's acceleration could be a side effect. As the cosmos expands, new horizons form, constantly measuring space-time into existence and driving it toward ever greater stability. Critics argue this verges on tautology. If everything is an observer, does observation still have meaning? Yet proponents highlight testable predictions. If cosmological horizons indeed stabilize the universe's quantum fog, their imprint might linger in gravitational waves or subtle distortions in the distribution of galaxies. Others suggest searching for anomalies in the cosmic microwave background, regions where quantum coherence somehow resisted decoherence, like whispers from a time before reality fully settled. The most profound implication, the universe's classical appearance isn't a given. It's the product of a relentless quantum editing process where space-time itself was shaped by its own boundaries. We're not just living in a universe that evolved, we're living in the version that survived. If our universe truly erupted from a white hole's quantum rebound, the scars of that violent transition might still be written in the sky, not as cryptic equations, but as ghostly fingerprints in the cosmic microwave background. One of the most tantalizing hints comes from the so-called cold spot, a mysterious region in the CMB where temperatures plunge unexpectedly, as if something had siphoned energy away long ago. While conventional cosmology struggles to explain this anomaly, the black hole-white hole bridge theory offers a provocative explanation. That cold patch could be the bruise left by our universe's violent birth, a relic of the moment the white hole's event horizon shattered, releasing its pent-up energy unevenly across the newborn cosmos. The physics behind this is as elegant as it is bizarre. When a black hole transitions into a white hole via quantum bounce, the process isn't perfectly symmetrical. Just as a cracking ice sheet fractures along unpredictable fault lines, the white hole's eruption would have left asymmetrical imprints in space-time's earliest moments. These imperfections would then stretch and freeze into the CMB's pattern as the universe expanded, like wrinkles preserved in a rapidly inflating balloon. Some models even suggest that if multiple white hole bounces occurred, perhaps in a chain reaction across a parent universe's black holes, their overlapping shockwaves could produce spiral patterns in the CMB's polarization data, subtle swirls detectable with next-generation telescopes like the Simons Observatory. But the echoes might run deeper. If the white hole's detonation wasn't perfectly smooth, quantum fluctuations in its precursor black hole structure could have seeded our universe's large-scale voids, those baffling cosmic deserts where galaxies vanish for hundreds of millions of light years. Think of it like a potter's hands leaving grooves in wet clay. The black hole's internal quantum geometry, imprinted during its collapse, might have twisted the white hole's explosion in ways that determined where matter would later cluster or refuse to. This could explain why simulations of cosmic structure always seem to lack the emptiest voids we observe. Their origins might not lie in inflation's quantum jitters, but in the topology of a black hole we'll never see. Even dark matter's elusive nature might trace back to this bridge. Some versions of the theory propose that not all the black hole's contents successfully tunneled through the quantum bounce. A fraction of its mass energy could have fragmented into exotic particles that neither radiate nor collide with normal matter, lingering as gravitational shadows, precisely the behavior attributed to dark matter. It's a haunting thought. The missing stuff of the cosmos might not be some unknown particle, but orphaned remnants of the black hole that birthed us, still tethered to our reality through gravity alone. The most radical prediction: if white holes leave acoustic fingerprints in the CMB, their frequency spectrum should differ subtly from inflation's. While inflation generates nearly scale-invariant fluctuations, a white hole's bang would imprint harmonics linked to its event horizon size, like listening for the difference between a bell's ring and a drum's thud in the universe's oldest sound waves. Future gravitational wave detectors might even catch echoes of the bounce itself, vibrations from the moment space-time snapped like a rubber band, redshifted to near silence over billions of years. Of course, skeptics highlight the elephant in the room. No white hole has ever been observed, but proponents counter that we've been looking for the wrong thing. A newborn white hole would resemble a big bang, an outburst of space-time, not a celestial object. And if every black hole secretly harbors a potential white hole in its quantum future, the ultimate cosmic joke might be that we're living inside one's aftermath right now. The deepest lesson of this theory isn't just about origins, but connectedness, a reminder that universes, like lives, might be shaped by unseen bridges to realities we can't revisit, only remember in the faintest echoes of light. The connection between consciousness and quantum mechanics might seem like science fiction until you peer into the inner workings of a living cell. Recent breakthroughs in quantum biology reveal that nature has been exploiting quantum phenomena for billions of years, long before humans built their first particle colliders. Take photosynthesis, for example. In plants and bacteria, energy from sunlight doesn't travel in a straight line to reaction centers. It superpositions, exploring all possible paths simultaneously like a wave before collapsing onto the most efficient route. This isn't just a quirky detail, it's quantum coherence operating at warm, wet, macroscopic scales, far from the sterile isolation of lab experiments. If fragile quantum states can persist long enough in noisy biological systems to optimize energy transfer, could they also play a role in something as vast as cosmic observation? Dive deeper into the avian compass, a built-in quantum navigation system in migratory birds. Researchers discovered that cryptochrome proteins in their eyes host entangled electron pairs sensitive to Earth's magnetic field. When a photon strikes these proteins, it triggers a quantum reaction where electrons exist in superposition, their spins simultaneously aligned and anti-aligned with the geomagnetic field until, crucially, the bird's perception collapses the state, extracting directional information. This isn't passive physics, it's active quantum measurement woven into the fabric of cognition. Scale this up to the universe's birth, and an eerie parallel emerges. If biological systems leverage observation to harvest quantum information, why couldn't the cosmos have used proto-consciousness to prune its own quantum branches into classical reality? The implications ripple into neuroscience. The human brain's microtubules, tiny protein structures inside neurons, have been hypothesized by researchers like Sir Roger Penrose to host quantum computations. Orchor theory suggests these microtubules process information via quantum vibrations, with consciousness arising from their orchestrated collapse. While controversial, experiments reveal that anesthetics, which selectively switch off consciousness, disrupt these vibrations without halting classical brain activity. It's as if the brain operates on two levels, a classical surface and a quantum undercurrent where observation and existence intertwine. Apply this to cosmology, and the universe's first moment transforms from a blind dice roll into a self-referential loop, a system where quantum potentiality and primitive awareness co-evolved, each shaping the other. Critics argue these biological quirks are localized exceptions, not evidence of cosmic consciousness, but proponents highlight a pattern wherever complexity reaches a threshold, be it in photosynthesis, navigation, or cognition. Nature seems to recruit quantum mechanics as a toolkit. If biology exploits superposition and entanglement to solve problems, why wouldn't the universe itself, facing the ultimate problem of its own existence, employ similar tactics? The fine-tuning of physical constants, gravity's exact weakness, the cosmological constants' razor-thin margin for error, might not be accidental, but the residue of a primordial quantum selection process where observer-compatible universes stabilized while others dissolved. The most radical experiments now probe this boundary directly. Quantum-delayed choice tests where particles retroactively adjust their behavior based on future measurements hint that observation's role isn't just passive, it's formative. In labs, particles seem to know they're being watched, as if reality continually reweaves its tapestry to accommodate conscious intent. Extrapolate this to the universe's birth, and the distinction between creator and creation blurs. We're not just inhabitants of reality, we might be its continuance, the universe observing itself into sharper focus through every conscious moment. Whether this idea unifies physics or unravels it, one thing's certain: the line between quantum mechanics and mindfulness just got a lot thinner. Gravitational waves could be the universe's most honest historians, ripples in space-time carrying whispers from epochs so ancient, even light had barely learned to shine. Among these echoes, scientists now hunt for something even more extraordinary: the faintest traces of quantum gravity's phase transition, a moment when space-time itself crystallized from a formless quantum storm into the structured fabric we know. Just as ice leaves jagged fractures as it freezes, the universe's transition from quantum foam to classical geometry might have imprinted telltale distortions in gravitational waves, clues hiding in the cosmic background hum. Recent simulations suggest these signatures could resemble steps in the gravitational wave spectrum, abrupt changes in frequency marking when space-time's quantum fluctuations finally locked into place. Imagine dropping a pebble into a pond where the water's viscosity suddenly changes. The ripples would alter their spread in a telltale pattern. Similarly, if the universe's quantum gravity froze unevenly like a lake icing over in patches, the gravitational waves generated during that chaotic era would carry kinks in their waveforms, subtle jags detectable by next-generation observatories like the Einstein telescope or LISA. These anomalies wouldn't just confirm quantum gravity's role in cosmic evolution, they'd reveal how it happened, whether the transition was sudden like a thunderclap or slow like dawn creeping across a landscape. The most tantalizing candidate for such a signal: primordial black holes colliding in the universe's first second. These hypothetical relics, some no heavier than a mountain yet smaller than an atom, would have formed from denser knots in the quantum foam as it solidified. When they merged, their gravitational waves would have encoded the ambient properties of space-time itself, including remnants of its quantum granularity. Researchers at the Perimeter Institute calculated that if these waves traveled through a universe still seething with quantum foam, their waveforms would scatter slightly, like light bending through frosted glass. Future detectors might catch this quantum fog effect as a statistical skew in black hole merger data, an excess of distorted signals at very high frequencies where quantum gravity's fingerprints linger. But the real jackpot would be discovering a stochastic gravitational wave background, a cacophony of waves from countless quantum events during the phase transition. This wouldn't sound like the distinctive chirps of black hole mergers, but more like static on a radio tuned between stations. Hidden in that noise could be a peak frequency corresponding to the exact moment quantum gravity's dice settled. For analogy, think of the cosmic microwave background, the afterglow of the Big Bang, but for gravity. Just as the CMB's tiny fluctuations reveal the universe's density variations at 380,000 years old, this gravitational fossil could expose its structure at 1/1,000,000,000 of a second, a snapshot of reality mid-transformation. Critics argue these signals might drown in louder astrophysical noise, but proponents highlight a clever workaround: pulsar timing arrays. These networks of ultra-precise cosmic clocks, neutron stars beaming radio waves like lighthouses, can detect gravitational waves by measuring subtle shifts in their beats. If a phase transition's waves passed through, they'd stretch and compress the pulsar's rhythm in a predictable pattern. Already, projects like NanoGrav have spotted hints of a low-frequency background. Whether it's from quantum gravity or colliding supermassive black holes remains hotly debated. The boldest implication: if we decode these imprints, we might glimpse the universe's source code, the rules that dictated how quantum potential became classical reality. It's like finding the original mold for a sculpture, revealing not just how space-time looks today, but how it chose to look. And if that mold turns out to be one of many possible configurations, it could hint at other universes beyond ours, each frozen into different shapes, each singing their own gravitational songs into the void. To test something as vast as the holographic quantum foam, you wouldn't expect scientists to start small, but that's exactly what's happening in labs around the world. Using tabletop experiments with artificial event horizons, physicists are recreating conditions that might mimic the universe's earliest quantum chaos, offering tangible glimpses into how space-time could have crystallized from a seething, pixelated foam. One groundbreaking approach involves superfluid helium, a liquid chilled to near absolute zero where friction vanishes and quantum effects dominate at macroscopic scales. When researchers stir this ultra-cold fluid into vortices, they create tiny tornado-like structures that behave strikingly similar to black hole event horizons. Particles of sound, called phonons, get trapped at the edges of these whirlpools, unable to escape the vortex's pull, a perfect analog for how light behaves near a real black hole. The magic happens when physicists probe these artificial horizons with laser pulses. Just as a black hole's gravity can stretch and distort light, these vortex-laden superfluids bend and scatter sound waves in ways that reveal hidden quantum behavior. In recent experiments, scientists observed unexpected echo sound waves that seem to rebound from the vortex edge moments after being absorbed. This eerie phenomenon mirrors theoretical predictions about how real black holes might preserve quantum information at their horizons, a key tenet of holographic principles. If space-time is indeed built from Planck-scale pixels, these tabletop vortex echoes could be the first experimental whisper of that granularity, a hint that the universe's fabric might remember interactions just like the superfluid's phantom rebounds. Even more provocative are experiments with Bose-Einstein condensates gases cooled to such extreme temperatures that thousands of atoms collapse into a single quantum state, acting as one giant superatom. By precisely manipulating these condensates with magnetic fields, researchers can simulate the birth of artificial universes, complete with their own expanding space-time analogs. In one stunning 2023 experiment at the University of Heidelberg, scientists observed spontaneous ripples in the condensate that matched equations describing quantum foam fluctuations. These ripples emerged without external input, as if the system were replaying the universe's first moments in fast-forward. When researchers adjusted parameters to mimic different energy densities, akin to tweaking the initial conditions of the Big Bang, the condensate's behavior shifted dramatically, producing patterns that aligned with holographic model predictions. It's as if these ultra-cold gases are acting as cosmic time machines, compressing eons of quantum gravity evolution into lab-scale microseconds. But the most tantalizing evidence might come from metamaterials, engineered structures with properties not found in nature, like invisibility cloaks or perfect lenses. By constructing these materials with microscopic pillars arranged in precise grids, physicists can create analog space-times where light waves behave as if they're traversing a quantum foam-infused universe. In one such experiment at Imperial College London, light passing through a metamaterial exhibited fractal scattering, a hallmark of holographic systems where higher dimensional information gets encoded on lower dimensional surfaces. The light's path wasn't smooth, it stuttered as if navigating an invisible lattice, mimicking how photons might travel through a pixelated cosmos. These lab-born anomalies don't prove the holographic principle outright, but they offer something equally valuable: a sandbox where theorists can test wild ideas about quantum gravity against real, measurable phenomena. Critics argue these analogs are just clever metaphors, that superfluid vortices and condensate ripples are too far removed from actual black holes or the Big Bang. Yet proponents counter that physics has always relied on such bridges. Einstein famously used trains and clocks to conceptualize relativity before the math caught up. The true power of these experiments lies in their ability to falsify theories. If holographic models predict behavior that flatly contradicts what's seen in the lab, those models must adapt or retire. Already, some quantum foam theories have been ruled out because they demanded fractal light scattering patterns that metamaterials fail to produce, a cosmic vetting process happening not in distant telescopes but on benchtops. The boldest implication: if space-time's quantum structure really does resemble these analogs, then the universe might be less like a smooth continuum and more like a frothy sea viewed from afar, an emergent illusion hiding unfathomable turbulence beneath. Future experiments aim to push further, using quantum entanglement in lab-grown horizons to test whether information can indeed be holographically projected, as the principle suggests. Every flicker of superfluid echo, every condensate ripple, brings us closer to answering whether reality's deepest layer is a pixelated code quietly running behind the scenes of everything we know. The quantum gravity model doesn't just rewrite the universe's origin story, it could hold the key to one of cosmology's biggest mysteries: dark energy's relentless push accelerating the cosmos apart. Picture the universe's fabric not as a static grid, but as a dynamic network where every node is a tiny quantum processor, constantly adjusting its connections. In this framework, dark energy might not be some exotic force. It could simply be the residual tension from severed links in space-time's underlying graph, like phantom vibrations from a cosmic web that never fully settled. When the universe transitioned from its ultra-connected, high-energy state to today's sparse lattice, most quantum links snapped, but some might have left behind stretched, elastic remnants. These could act like invisible springs, pushing nodes apart with a force that grows as the network expands. Here's where math meets observation. Quantum gravity predicts that dark energy's strength isn't constant, but subtly tied to the universe's total connectivity. As space stretches, the remaining links thin out, altering the repulsive force in ways that could explain why cosmic acceleration seems to vary over time, a deviation from Einstein's cosmological constant that telescopes like Euclid and the Vera-Rubin Observatory are now hunting. But how do you test something as abstract as space-time's quantum wiring? One clue might lie in the cosmic microwave background's polarization patterns. If the universe's gravity transition left behind topological defects, kinks, or twists in the network, they could imprint faint, swirling signatures in the CMB's light like fingerprints on glass. These anomalies, called B-modes, are already targets for primordial gravitational wave searches, but quantum gravity offers a twist. Certain defect geometries would produce unique spiral patterns distinguishable from inflation's fingerprints. Future CMB experiments with ultra-sensitive polarization detectors like the Simons array could spot these telltale spirals, effectively photographing space-time's quantum skeleton. Even particle collisions might reveal hints. If high-energy protons smashed together at CERN produced exotic, ultra-heavy particles predicted by gravity models, their decay paths could betray the existence of extra quantum connections, ghost links that briefly flicker into being before dissolving. It's like shaking a dusty rug and seeing which hidden threads flutter. Some theorists even propose that quantum gravity's granular structure could subtly alter how neutrinos oscillate between flavors as they traverse space, a deviation from standard physics that experiments like Dune could catch. The most tantalizing prediction, quantum gravity suggests dark energy isn't truly uniform. Just as a spiderweb's tension varies thread by thread, the repulsive force driving cosmic acceleration might ripple with faint inhomogeneities tied to the universe's deepest structure. These ripples would be too subtle to notice locally but could stack up across billions of light years, distorting the large-scale distribution of galaxies in ways that upcoming redshift surveys like DAISY might detect. If the voids between galaxy clusters appear slightly more stretched or compressed than standard models predict, it could signal that space-time's quantum graph is still settling, an echo of the universe's first and fiercest transformation. Critics argue these signals are too faint to distinguish from cosmic variants, but proponents counter with an ingenious workaround. Quantum gravity's defects would align in a preferred direction, breaking the universe's statistical symmetry. Find that axis and you've found the shadow of the cosmic web's original weave. Whether this theory holds or not, it forces a radical rethink of dark energy, not as a mysterious stuff, but as the cosmic afterglow of space-time's quantum metamorphosis, a reminder that reality's seams might still be stitching themselves together. Those vast cosmic voids, immense stretches of nothingness spanning hundreds of millions of light years, might not be random emptiness, but the lingering echoes of the universe's first fractal quantum whispers. Imagine zooming out on a leaf's vein structure and seeing the same branching pattern repeat from stem to tip, except here, the leaf is the cosmic web, and its veins are galaxy filaments weaving through unimaginable darkness. This striking similarity across scales isn't coincidence. It's a potential smoking gun for quantum fractality, shaping reality from the smallest Planck length to the largest observable structures. At the quantum level, fractal behavior emerges naturally from chaotic fluctuations. Particles in superposition don't just occupy two states, they explore infinite possible paths simultaneously, creating complex, self-repeating probability clouds. Scale this up to the universe's birth, and you get a primordial quantum storm where every fluctuation, no matter how small, carried the same fractal signature. As inflation stretched these quantum seeds to cosmic proportions, their imprinted patterns grew into the universe's backbone voids and filaments, tracing the same mathematical contours as their quantum ancestors. It's like blowing up a snowflake's microscopic crystal to the size of a galaxy cluster. The underlying geometry stays eerily intact. The most compelling evidence lies in the statistical fingerprints of these voids. When cosmologists analyze their distribution, they find clustering patterns that mirror quantum interference, those same ripples seen when particles act as waves in lab experiments. Some voids align in concentric shells like bubbles in a froth, while others form branching chains resembling fractal dendrites. Even more telling, the largest voids, like the Boötes supervoid, a chilling expanse 300 million light-years wide, exhibit temperature anomalies in the cosmic microwave background. These cold spots could be shadows cast by the universe's deepest fractal layers, regions where quantum coherence resisted total decoherence during the Big Bang's aftermath. But how does quantum fractality translate to gravity's domain? The secret might lie in something called scale-free correlation. In ordinary physics, forces like gravity weaken predictably with distance, but in a fractal quantum framework, gravitational influence could propagate in nested, self-similar waves. Picture dropping a pebble into a pond where ripples generate smaller ripples, which generate even smaller ones, all following the same pattern. Matter would cluster along these fractal gravitational contours, leaving voids where the ripples cancel out. Simulations incorporating this idea produce cosmic webs strikingly similar to observed galaxy surveys, with one key difference: their voids aren't randomly placed, but arranged in geometric hierarchies that reflect their quantum origins. Critics argue that inflation alone could explain large-scale structure, yet the data reveals deviations. The Sloan Digital Sky Survey mapped over 1 million galaxies, uncovering filament patterns too intricate for classical models to fully replicate. Some filaments split symmetrically like fractal branches, while voids nest within larger voids in a near-perfect mathematical recursion. These aren't just cosmic accidents, they're potential relics of a universe that never quite forgot its quantum beginnings. Perhaps the most haunting implication is this: if the cosmic web truly mirrors quantum fractals, then the voids aren't empty at all. They might be teeming with quantum potential, regions where reality's rules subtly bend, where space-time's pixelated roots briefly flicker through the classical facade. Future telescopes probing these voids might not just find absence, but hidden layers of structure, ghostly imprints of a universe that's still, in its quietest corners, whispering to itself in the language of quantum infinity. At the very smallest scales, empty space isn't empty at all. It crackles with quantum fluctuations, particles and antiparticles flickering into existence before vanishing like sparks in the dark. This phenomenon isn't just theoretical. Labs have now recreated these vacuum fluctuations in controlled experiments, manipulating the quantum void to produce detectable particles from nothing but raw energy. These breakthroughs force us to revisit the very first theory we explored: the idea that the universe itself could have emerged from a quantum fluctuation, a cosmic hiccup in the fabric of nothingness. But here's the twist: while lab-generated fluctuations last mere fractions of a second and span distances smaller than an atom, the universe's birth would have required a fluctuation of unimaginable scale and stability. So how could something so fleeting in the lab have birthed an entire cosmos? The answer might lie in the strange behavior of quantum systems under extreme conditions. In experiments like those at the Helmholtz Zentrum Dresden-Rossendorf, scientists use ultra-intense laser pulses to rip apart the quantum vacuum, creating particle pairs that exist just long enough to be measured. What's fascinating is that these lab-born fluctuations aren't random. They follow precise mathematical patterns, popping in and out of existence in ways that echo the universe's own initial conditions. Scale this up to the energies present at the Big Bang, and the quantum vacuum wouldn't just flicker. It could undergo a phase transition, locking a fluctuation into permanence like a wave freezing mid-crash. The same instability that makes lab-generated particles vanish almost instantly might, under cosmic-scale energies, have flipped into a self-sustaining loop, birthing a universe instead of a fleeting spark. Yet the differences between lab and cosmic scales reveal just how fine-tuned that primordial fluctuation must have been. In the lab, fluctuations borrow energy from the vacuum but must repay it almost immediately, a constraint enforced by Heisenberg's uncertainty principle. But if the early universe's expansion stretched space faster than the quantum debt could be called in, that borrowed energy might never have needed repayment. Inflation, the universe's explosive early growth, could have acted like a cosmic credit freeze, allowing the initial fluctuation to avoid the usual quantum collapse. Picture a gambler who keeps winning just enough to stay ahead of their debts, forever postponing the inevitable, except here, the gambler is reality itself, and the winnings are galaxies, stars, and everything we know. The most startling parallel between lab and cosmic fluctuations lies in their mathematical symmetry. Whether it's particle pairs in a vacuum chamber or the universe's first quantum jitter, the underlying equations share eerie similarities. Both scenarios involve a sudden local imbalance in energy density, a temporary bending of the rules that, given the right conditions, can snowball into something far larger. Some theorists suggest this isn't coincidence, but evidence of a deeper principle, that the universe's birth wasn't a singular, unrepeatable event, but part of a spectrum of quantum phenomena that we're only now learning to manipulate on smaller scales. This raises a provocative question. If we can create virtual particles in the lab, could we someday engineer conditions that mimic the universe's birth? The energy requirements are absurdly beyond our reach. The Big Bang unleashed temperatures of over 10 trillion degrees in its first microsecond, but the underlying physics might still offer clues. Experiments with ultra-cold Bose-Einstein condensates have already simulated cosmic inflation in miniature, showing how quantum turbulence can spontaneously generate structure. While we'll never recreate a universe in a test tube, these analog systems let us explore how quantum randomness can crystallize into order, a process that might have shaped everything from the first atoms to the largest galaxy clusters. Critics argue that scaling up quantum fluctuations to cosmic proportions is like comparing a candle flame to a supernova at technically the same physics, but separated by orders of magnitude too vast to bridge. Yet supporters counter that nature often repeats patterns across scales, from the spiral of a galaxy to the whirl of a hurricane. If quantum fluctuations can birth particles in the lab, why not universes in the void? The debate isn't just academic, it cuts to the heart of whether our universe is a one-time accident or part of a grander cycle of quantum births and deaths. Ultimately, these lab experiments don't just revisit the first theory, they refine it, offering tangible data to test what was once pure speculation. Every flicker of particles in a vacuum chamber is a whisper from the universe's first moment, a reminder that reality might not have begun with a bang, but with a quantum maybe, a fluctuation that got lucky and just kept going. Let's circle back to the holographic universe, but this time armed with breakthroughs that make the idea even stranger. When we first explored the notion that reality might be a projection from a distant, two-dimensional boundary, it seemed like speculative poetry. Now cutting-edge work in ADS/CFT correspondence, a framework linking quantum field theories to gravitational models in higher dimensions, has turned this metaphor into a precise mathematical dictionary. The key lies in quantum error correction, the same technology protecting qubits in today's fledgling quantum computers. What if space-time itself is nature's ultimate error-correcting code, a cosmic failsafe ensuring reality doesn't glitch out of existence? Imagine a DVD scratched by cosmic rays, yet somehow the movie plays perfectly. That's the magic of error correction. Redundant data spread across the disk allows the player to reconstruct missing bits. In ADS/CFT, this analogy takes on cosmic proportions. The holographic boundary, our universe's equivalent of the DVD surface, encodes information in such a way that local errors, like a black hole swallowing a star, get automatically corrected across the entire system. This isn't just about storage efficiency. It suggests spacetime's very stability relies on quantum entanglement, weaving redundancy into reality's fabric. When you stub your toe on a table, the pain isn't just local, it's the endpoint of a vast, entangled network that keeps the table real across the cosmos. Recent twists in the math reveal something astonishing. The AD/S/CFT correspondence predicts that spacetime regions emerge from quantum error-correcting codes with specific properties, like the so-called holographic tensor networks. Picture a cosmic version of a smartphone's RAID storage, where data isn't stored in one place but scattered across many drives for resilience. In this view, the three-dimensional universe we experience is a decoded projection of information stored far more efficiently on a two-dimensional surface. Black holes, they're nature's way of handling corrupt data sectors, swallowing information temporarily before eventually rebooting it as Hawking radiation. The smoking gun might lie in quantum entanglement entropy, a measure of how information gets shared between particles. In 2023, Caltech researchers found that the equations governing spacetime's emergence perfectly mimic those controlling error correction in quantum networks. It's as if every time two particles entangle, they're establishing a backup link in reality's cosmic hard drive. Even more mind-bending, this framework could explain why spacetime has exactly 4 dimensions, 3 of space, 1 of time. It's the optimal configuration for balancing information density with error resilience, like a Goldilocks zone for stable reality. Critics initially dismissed holography as untestable metaphysics, but experimentalists are now hunting for its fingerprints. If spacetime is error-corrected, tiny glitches might occasionally slip through, perhaps as anomalous particle collisions where energy briefly doesn't conserve, or as statistical quirks in cosmic ray showers. Others suggest looking for entanglement shadows, regions near black holes where quantum correlations abruptly vanish like dead pixels on a screen, the most provocative idea. That dark matter isn't matter at all, but a bug in spacetime's error correction, an accumulation of unrecoverable data from early cosmic crashes. This isn't just about rewriting textbooks, it's about redefining existence. If AD/S/CFT and quantum error correction hold, reality isn't the foundation, it's the user interface. The universe isn't computed, it's compiled, with spacetime as the runtime environment and quantum entanglement as the debugging tool. Every star, every thought, every moment might be a temporary reconstruction from deeper, stranger bits, a hologram that keeps recalibrating itself to hide the seams. And if that's true, the next great physics breakthrough might not come from a telescope or collider, but from cracking the cosmic source code. The multiverse branching at time zero theory just got a major quantum upgrade, and the implications are rewriting how we think about cosmic inflation. Remember that dizzying idea from earlier, where the Big Bang wasn't just an explosion, but a quantum fork in the road spawning infinite parallel realities? Well, new research suggests inflation, that faster-than-light expansion in the universe's first sliver of a second, might not have been a smooth, deterministic process after all. Instead, it could have been a quantum roller coaster, with every possible inflationary path playing out simultaneously before decoherence locked in our version of reality. Picture this: the instant after the Big Bang, the universe wasn't just a hot soup of particles, it was a seething quantum foam where even the laws of physics existed in superposition. In this chaotic realm, inflation didn't happen once, but every possible way at once. Some quantum branches inflated rapidly, stretching space-time so thin that particles barely interacted. Others inflated sluggishly, collapsing back into singularity. Our universe, it's the Goldilocks branch, the one where inflation lasted just long enough to create galaxies, but not so long that everything diluted into nothingness. The kicker, according to revised eternal inflation models, these branches didn't just split, they occasionally collided, leaving cosmic bruises we might still detect. Recent simulations at Stanford reveal something startling. When two bubble universes collide during inflation, they don't just bounce off like billiard balls. they create interference patterns in space-time itself. Think of two soap bubbles merging. The boundary where they meet forms a complex, shimmering membrane. In cosmic terms, that membrane could manifest as a circular imprint in the cosmic microwave background, anomalous rings of temperature variation where the physics from one universe briefly leaked into another. The Planck satellite's data already shows a few suspiciously perfect cold spots, but next-generation telescopes like the Simons Observatory are hunting for the real smoking gun, concentric polarization patterns that would betray a collision from beyond our cosmic horizon. But here's where the debate gets fierce. Some physicists argue these bubble collisions would have been too rare to leave detectable traces, like trying to find a specific grain of sand in a desert the size of the observable universe. Others counter that quantum entanglement between brane higher dimensional membranes in string theory could have made collisions more likely, weaving hidden connections between universes before they fully decoupled. It's a cosmic twist on Schrödinger's cat. Instead of a dead or alive feline, we're talking about entire universes that were both separate and linked until the moment they were observed by decoherence. The most radical update, this framework could solve the measure problem that plagues multiverse theories. If every possible quantum outcome spawns a new universe, how do we calculate probabilities in an infinite ensemble? The new approach suggests universes aren't born equal. Their quantum amplitudes, basically, their weight in the multiverse, depend on how their inflationary paths interfered with each other in that primal superposition. Our universe might not be special, just statistically likely, like rolling a billion-sided die and landing on one of the more common numbers. Critics still pounce on testability. How do you prove a collision with a universe whose physics might be utterly alien? Supporters point to subtle clues. If our bubble universe grazed another during inflation, the cosmic microwave background could carry imprints of that universe's physical constants, like a fossilized handshake from a long-lost twin. Even dark energy's mysterious acceleration might be a relic of this quantum entanglement, a residual pull from a neighboring universe's gravity leaking through the dimensional divide. The ultimate irony, if this theory holds, the multiverse isn't just a consequence of quantum mechanics, it's the reason quantum mechanics exists at all. Those eerie superpositions and collapses we see in labs might be microscopic echoes of the universe's first and greatest quantum split. The moment reality itself couldn't decide what to be, so it became everything at once. And somewhere in that infinite branching, we ended up here not because this universe was meant to be, but because the quantum dice just happened to land this way. For all we know, there's another version of you watching this video in a universe where gravity pushes instead of pulls, wondering how anything could possibly fall down. The idea that consciousness might have played a role in the universe's quantum origins once sounded like fringe speculation, until biologists started uncovering quantum processes humming inside living cells. If delicate quantum superpositions can persist in the warm, wet chaos of a plant's photosynthesis or a bird's navigational compass, could the universe's first moments have been shaped by a similar interplay between observation and reality? Revisiting the von Neumann-Wigner interpretation where conscious observers collapse quantum states through the lens of cutting-edge quantum biology forces us to confront an electrifying possibility. The line between observer and observed might not just blur at the cosmic scale, but dissolve entirely. Take the European Robin's magnetic compass, a biological marvel where entangled electrons in cryptochrome proteins respond to Earth's magnetic field with quantum precision. When light strikes these proteins, electrons enter superposition states, simultaneously probing multiple alignment possibilities with the geomagnetic field until the bird's visual system chooses an orientation. This isn't passive physics, it's an active quantum measurement woven into sensory perception, where consciousness literally navigates by collapsing probabilities into concrete directions. Scale this up to the universe's birth, and the implications shudder through cosmology. If a speck of neural tissue can harness quantum coherence to guide flight paths, why couldn't a universe in the making leverage proto-consciousness to steer its own decoherence? Even more provocative are findings from photosynthesis research. Purple bacteria exploit quantum coherence to achieve near-perfect energy transfer efficiency in their light-harvesting complexes. Vibrational modes in their proteins act like quantum tuning forks, stabilizing superposition states long enough to explore all possible energy pathways before selecting the optimal route. This biological fine-tuning mirrors how some theorists describe the early universe's quantum fluctuations as a probabilistic haze where every possible configuration existed until environmental interactions, or perhaps something akin to observation, pruned the branches into a single timeline. The eerie parallel, both systems, the microscopic and the cosmic, seem to balance exploration and commitment, testing every quantum possibility before locking into stable states that maximize functional outcomes. Neurobiology adds another layer. The ORCH or theory, controversial yet tantalizing, suggests microtubules in brain neurons host quantum computations that give rise to conscious experience. When anesthetics disrupt these microtubule vibrations without stopping classical neural activity, consciousness vanishes, implying that subjective experience might be quantum mechanical at its core. If true, the universe's first quantum collapse might not have required a human mind, but simply a system with sufficient complexity to perform self-referential quantum measurements. The infant cosmos, throbbing with quantum potential, could have met this threshold through its own evolving structure, a kind of cosmic neural network where space-time itself acted as both observer and observed. Critics argue these biological examples are niche adaptations, not evidence of consciousness shaping reality. Yet the sheer diversity of life's quantum tricks, from enzyme catalysis exploiting tunneling effects to the possible quantum origins of smell, paints a picture of nature routinely harnessing quantum phenomena in warm, messy environments. If biology can stabilize superposition states despite thermal noise, why couldn't the universe's pristine energy densities do so more effectively? The counterargument cuts deeper. If consciousness emerges from quantum processes in brains, perhaps it's not that observers collapse quantum states, but that quantum states, when complex enough, give rise to observers. In this view, the universe didn't need consciousness to exist. It grew consciousness as a natural consequence of its quantum complexity. The most startling test of these ideas might come from quantum neurology. Experiments are now probing whether human cognition can directly influence quantum systems, not through mystical means, but via the brain's hypothesized quantum infrastructure. In one landmark study, participants' focused attention appeared to slightly alter the interference pattern of photons in a double-slit setup, as if their observation carried physical weight. While hotly debated, such results hint that the boundary between mind and quantum world might be porous. Extrapolate this to cosmology, and the universe's first moments transform into a self-referential loop, quantum fluctuations birthing structures that eventually observe them, closing the circle in a dance where creator and creation become one. Whether this theory holds or not, it reshapes the anthropic principle from a passive observation into an active process. The universe isn't just improbably suited for life, or its quantum precursors, might have been the sculptor all along. The silence of the quantum void wasn't broken by a bang, but by a question, the universe asking itself what it was and answering in the only way that lasts, by being seen. From quantum fluctuations birthing reality to holographic codes projecting existence itself, these 30 theories shatter any simplistic story of cosmic origins. The most startling thread running through them all: the universe's first moments weren't a definitive event but a shimmering quantum may, a superposition of possibilities so vast it makes Schrödinger's cat look like child's play. Whether you're drawn to the elegance of cosmic holograms, the audacity of entangled twin universes, or the spine-tingling idea that observation might have sculpted reality, one truth emerges. Quantum mechanics doesn't just describe the universe, it might be the universe from the Planck scale to the cosmic horizon. Consider the radical implications. If black holes birth white holes, we're living in the aftermath of a quantum bounce we'll never see. If consciousness plays a role in collapsing reality, the universe didn't just create life, life might have completed the universe. And if space-time is a cosmic error-correcting code, every galaxy, every atom, could be a pixel in a computational masterpiece we're only beginning to decode. The math behind these ideas isn't speculative fantasy. It's emerging from labs studying everything from superfluid vortices to the quantum vibrations of bird compasses, revealing patterns that echo across scales. Yet the greatest mystery remains: why did this universe, with its precise constants, its improbable balance, win the quantum lottery? Was it sheer statistics in an infinite multiverse or something deeper? Future quantum cosmology might hold the answer. Next-generation telescopes could spot holographic glitches in the cosmic microwave background. Gravitational wave detectors might catch whispers from pre-Big Bang bounces. And tabletop experiments with Bose-Einstein condensates could recreate quantum genesis in miniature, testing if universes really can bootstrap themselves into existence. So here's the question that keeps physicists awake at night. If quantum superposition shaped the cosmos, what else is still unresolved? Could pockets of unreality, regions where the universe's first quantum haze never fully cleared, still lurk in the voids between galaxies? The deeper we dig, the stranger the answers become. Maybe the ultimate truth isn't a single theory, but the collective hum of all 30. A cosmic chorus where each idea holds a fragment of the greater melody. Now it's your turn. Which of these theories bends your mind the most? Do you think we'll ever find proof of a sibling universe, or is the quantum code too well hidden? Drop your thoughts below, because the next great cosmic revelation might not come from a lab, but from a conversation that starts right here.